Hello, this is part two of my discussion on steady state error. I started at the initial screen, so let me just scroll down to where we were. So that was the explanation that I just gave with this practical example of a cruise control on a car going up a hill is the practical way to understand it. But I want to look inside, and so I'm going to give a block diagram description of what's going on. Our block diagram is shown here with the components arranged in the order that you see them. We compare the desired value, R, with the actual value, C, and then that result, subtracting the C from the R, the actual value from the desired value, we get the error value, which goes into the controller. The controller then talks to the actuator, or tells the actuator, sends a command to the actuator that will change the value of the plant, the thing that we're trying to control. So we can change the value of C by sending a non-zero signal to the actuator, which then does something to make the plant respond. If this were the car, the example that we just had, this would be the controller for the cruise control. This would be the throttle plus the engine, if you want to consider the engine as part of the actuator, and then this would be the car itself. But let's look at it more abstractly than that. All I have here is I have a plant that is a first order system. And have an actuator that's a gain. That's often the case. And then I have a PID controller, but the I part and the D part are zero, so it's a P only controller. So this is a first order closed loop system. And then we can, the other thing I didn't show in here is I don't show the sensor. This is a unity feedback loop, and many computer control systems are like that. They do have a sensor, but once you send the voltage or the current from the sensor back into the computer that's doing the control, it's immediately converted back into whatever was being measured. So you'd have, for instance, if it was a car, this would be a speed that's being measured, and it would produce a voltage depending upon the speed. That voltage would go to the computer, and the computer would immediately convert it back into the speed. So in effect, the total result of all that is that the speed that goes into the computer, that's inside the computer, is equal to the real speed of the car. It could be pressure, temperature, or whatever. All of the sensors work substantially the same way. So we have a unity feedback system, which is, like I said, is very common in a computer control system. It's a first order system, so we have in the feed forward path of this system, we have three components. Two of them are just simple gains. So we can actually collapse this into one big feed forward block, which I've done here just simply by getting the Kp and the Ka and multiplying them together, and then times the numerator of the plant, the gain of the plant. So I go from this step to this step, and that's just pure block diagram algebra. And then we can get the closed loop transfer function. So what that means is if we wanted to replace this entire system right here with a single block, we have a formula for doing that. And this is the formula that you'll see in my book. The N stands for numerator, the D stands for denominator. And I think later on, this formula should be known, but let's see, I think maybe in the next slide. No, not there, not there. Let's see. Yeah, here. The G refers to the feed forward part of the plant, and the H refers to the feed back part of the plant. So NG is the numerator of G, and DG is the denominator of G. NH is the numerator of the feedback part, and DH is the denominator of the feedback part. So let me go back up to where I was. That's what are in these formula. Now, if we have a unity feedback system, which we have here, the H part is just 1, and 1 is equal to 1 over 1. So NH is 1 and DH is 1. So in our formula, anything with an H on it is just 1, and it goes away, and we wind up with a simpler formula for a unity feedback system. Now, I can substitute these values from our loop. Here we go. Here's our G. Our H is 1, so we can use the simplified formula. And I substitute them in there. So you can flip back and forth here, or I can flip back and forth here. The NG is are these three terms together, and the DG is this TS plus 1. So I have NG there. This is DG plus NG, which is that again. So I have two NGs, and then the DG is there in front of it. Now, when you have it, this is a first order system. It has a S to the first power in the denominator, and that makes it a first order system. But normally when you have a first order system, you want it in the standard format for a first order, which is this is actually the standard format for a first order. What characterizes it is that the non-S term has a 1 there. It's not anything but 1. Now, if we look at the non-S term in our formula, we have a 1 there, but we also have this. This is not any part of S. So we want this whole thing right here to be 1. And the way to make the whole thing equal to 1 is to divide the top and the bottom by that value, and I do that in the next step. Oh, sorry, here. I divide the top by 1 plus Kp times Ka times K, and I do the same thing on the bottom. And so I wind up with it in standard form now. I have a 1 right here. And with it in standard form, when I have the 1 right here, then the top, the numerator is the gain, and the coefficient of S in the denominator is the time constant. So this is the closed loop gain, and this is shown down here in the next step. That's what's on top. And then this is the closed loop time constant. That is the coefficient of the S term. So this shows really what happens to the loop when you close it. So closing the loop has the effect of changing the steady state gain of the closed loop system, and also changing the time constant of the closed loop system. But what's important here is this, and here we go back to our Rolling Stones title. You can't always get what you want. What we just saw is we saw that the closed loop steady state gain is equal to this expression, but this is not equal to 1. Excuse me. I have this 1 right here, and that screws it all up. So actually, as you can tell, since I'm getting NG and I have NG here also, adding this 1 in here means that KCL is going to be less than 1 altogether. Now, what that means, or the result of that is, if I want what I have to be equal to what I want, then the steady state gain of the closed loop system needs to be 1, and it's not. So because the steady state gain of the closed loop system is not 1, then C will not be equal to R. What you have will not be equal to what you want, except for the single case of all of these things being 0. So that's what we just saw, and the problem is that we have nothing. We have a very simple controller, a P-only controller, and the result of that is that we will have steady state error. I'm going to stop here and start over again at this point because we're close to 10 minutes, and I don't want any of these to be greater than 10 minutes. So see you soon.